So starting with our position versus time graph, I'm asked to find the distance and displacement. Distance is going to be the total distance traveled, so I'm going to mark off the different sections. So this first part, I'm going from 0 to 8, so this section would be like 8 meters. Right here, I'm at rest, so that would be 0 meters traveled. And then I'm going from 8 back to 0, so that is another 8 meters traveled. To find the distance, I'm adding it all up. 8 plus 0 plus 8 is going to give me 16 meters. Now for displacement, what we care about is the starting position and my ending position. So I'm starting at position 0 and I'm ending at position 0, so that would be a change of 0. Oops. All right, our velocity at 3.5 meters per at 3.5 seconds. So I'm looking at this little section right here, because when I asked to find instantaneous velocity at a point, really that's just saying of the section, because we don't know how to find velocity at a point. So if we're looking at this section, you can do 0 meters divided by 3 to 4 is 1 second, which is going to give me a velocity of 0 meters per second. Or you can say, well, that's flat, that's just at rest, so the velocity would be 0. Now, when we look at 6 seconds, again, we can't find velocity at a point, but I can do for this whole section right here that's straight. So, oops, we already know 8 meters, and now it's just looking at time from 4 to 8 seconds. So 8 meters, 4 to 8 seconds took 4 seconds, so that is going to be a velocity of 2. Now it's going backwards, which is why I have a negative sign right there, but you should at least get this 2. If you see a negative, you're like, oh yeah, it's because it's going backwards. We've got a Jaguar that leaves skid marks that are this many meters in length. Meters, that tells me that is a distance. Assuming that the Jaguar skidded to a stop, that means that the final velocity would be 0. Constant acceleration of negative 3.9 meters per second squared, that is my A. I want to know the speed before, so speed or velocity, that would be V. The velocity beforehand is going to be I. So then now I'm just picking the equation that has those 4 letters. Both velocities A and D. The only equation that works is my last one. Now it's just plugging in, 0 squared, VI is what I'm looking for, to A, distance. Now these 3 can all just be multiplied together. These 3 are going to make minus 2262, and then I still have the VI squared, and it's still equal to 0. So this is just 3 numbers multiplied, you just put it in your calculator. Now, I'm going to add this term over, because I'm trying to get VI by itself, so when I add that one over, you get 2262 equals VI squared. And the last step is to get rid of that square because I want VI by itself. So we're going to take the square root, and that's going to give me an initial velocity of 47.56. Oops. 3, a stone is dropped into a 50-meter deep well from rest. So 50 meters, that is my distance. From rest, initial velocity is 0. I want to know the time that it takes to hit the bottom, so looking for time, and you know your acceleration is 9.8. So then picking the equation of these 4 letters, you should be picking D equals VIT plus 1/2 AT squared. The other 2 do not work because I don't have VF, and I'm not looking for it, so it's irrelevant. Now 0 times T is just going to go away. 1/2 of 9.8, put that in your calculator. 1/2 of 9.8 is just 4.9. T squared is still there. 50 is still there. I want to get T by itself. I am going to have to get rid of the square, but before that, I need to get rid of the 4.9. So then that's going to give me like 10.2 is T squared. And then now, last thing I should do is get rid of that squared by taking the square root. So then my time is 3.19 seconds. 4, I am asked to find the acceleration from 4 to 6 seconds. So from here to here. I have a graph of velocity and time, and I'm looking for A. So the equation that relates velocities, time, and A is, oops, it's a plus sign, VF equals VI plus AT. And now I'm just looking. So my final velocity of this section, that would be at the end, was 2. Initial velocity of the section, that was right here, is 0 plus A. What I'm looking for in 4 to 6 seconds, that's 2 seconds. So basically 2 equals A times 2. So then my acceleration is just 1. the acceleration between 6 and 9 seconds. So in here, you could still do the same thing, plug into your equation. Vf equals Vi plus At. Initial velocity is 0, or not 0, sorry, 2. Final velocity is 2. Looking for acceleration, 6 to 9 seconds, that would be 3 seconds. First thing I would do would move this 2 over, and then you would get 0 equals A times 3. Divide by 3, you're still getting 0. Or you could have said, oh, that is moving at a constant velocity. If you have a constant velocity, then you are not accelerating. Your acceleration should be 0. C is asking how far the car traveled from that 6 to 9 seconds. Well, we just said that this would be at a constant velocity. And I'm looking for how far. How far would be distance. I know that the velocity is 2 all of that time. And 6 to 9 seconds, we know the time would take 3 seconds. We're looking at constant velocity, so we are able to use our V equals D over T, and that's going to help me find distance. Velocity, make sure you plug in the velocity for velocity, not into distance. So V goes with the V, or 2 goes with the V. Looking for D, time is 3, and then we're going to multiply up to get distance by itself, like that, and your distance is 6 meters. 4 to 6 seconds. Going up on a velocity graph means I'm speeding up. From 9 to 10 seconds, going down on a velocity graph means I am slowing down. And then here we already said that was constant velocity. A child left home, started walking at a constant velocity. After a time, she stopped for a while and then continued with velocity greater. All of a sudden, she turned around and walked very quickly back home, which represents her distance versus time, or her position versus time graph. So let's say she started at home, so home would be like 0, so they're all starting at 0. She walked forward, constant velocity, that would be straight. She stopped for a while, that would be staying in the same spot, resting. And then she continued on, so she's not turning around and going backwards yet. She's going to continue on with a greater velocity. Going faster is going to look steeper, so yeah, that's excessive, but steeper. And then all of a sudden she turned around and she walked home very quickly, so that would also be steep right there. So I want going up, staying for a little while, going up again, and then coming back. So the only one that goes up, rest, goes up, and then comes back was B. Six, we've got a ball that is rolling 2 meters per second towards the back of a moving train, and to an outside observer, it looks like the ball is moving 27 meters per second north. So I've got a train. I'm going to guess that the train is moving north. So the train is moving north. I am looking for what the velocity of the train must be. So I'm looking, I don't know what this velocity is, but I do know that inside a train, a ball is going towards the back. And I do know that to an outside observer, the ball looks like it is going 27. So it looks like 27 this way. Now going to the back, sorry, that's a terrible arrow, that's going the opposite direction. I know if I were given this velocity, that what I would have done is I would have said, okay, this velocity minus 2 to get what this one is. So then now you're just thinking, okay, what velocity must the train be going with if I subtract 2 and it looks like 27? So your answer should be that this is 29 meters per second. And then just double check, okay, if I have a train that's going 29 north and a ball goes to the back at 2, then yeah, that would look like 27 to somebody else. Now, if you're like, wait, but I thought we subtract these two numbers. No, you do subtract the velocity of the train minus the velocity of whatever's going to the back. That's not the two numbers that I gave you. I gave you what the answer was. We had to work backwards. What minus 2 would give me 27, which is where I'm getting 29 from. Okay, 7 is a velocity versus time graph. 0 to 3. So 0 to 3 right here. We want to know how far it moved. That's looking for distance. We're talking about constant velocity in here, so I'm going to use V equals D over T. The velocity, let's look. This is 2, 4, 6, 8, so this is 8 right here. Looking for distance, 0 to 3 seconds is obviously 3 seconds, and then now I would just multiply up. That would give me my distance is 24 meters. Acceleration from 3 to 6, that's this one right here. So I'm going to use my equation with velocity and time to get acceleration. So VF equals VI plus AT. VF would be at the very end, so this is -2, -4 right here. Initial velocity for this section is up here at 8 plus a, and then 3 to 6 seconds is taking 3 seconds. So the first thing, I need to combine my like terms, so I'm going to subtract this 8 over. 4 minus 8 is going to give me negative 12 equals a times 3. And then now I can divide that 3 over, I get acceleration is negative 4. How far did it move from 6 to 10 seconds? So then, now I'm back at a constant velocity of negative 4, so still looking for distance. This is constant velocity, so I can use this equation to find the distance. Velocity is negative 4, distance I'm looking for, and 6 to 10 seconds, that would be 4 seconds. Multiply up, so your distance is negative 16. The negative just means that it was in the negative direction because you've got a negative velocity, like going backwards 16 meters. The acceleration in the first 3 seconds. So if I'm looking in the first 3 seconds, I'm looking for acceleration. My initial velocity was 8, my final velocity was 8. So if you were to plug into our equation to solve for a, we've got 8 equals 8 plus a 3 seconds. Subtract the 8 over, you get 0 equals a times 3. Your acceleration is 0, which again you could have told me because it's at a constant velocity. You do not have an acceleration. Okay, position versus time graph. When is at rest? So at rest is staying in the same position. So that would be from 0 to 3. And again from 4 to 7. When is it moving at a constant speed? So here it is moving at a constant speed. It's moving backwards at a constant speed, but constant speed nonetheless, 3 to 4. And when is the speed changing? So on a position graph, a speed changing or an acceleration would look like a curve. So in this case, this one is curved. It ends up getting steeper, so it's actually speeding up right here. So my speed is changing from 7 to 8 because it is curved, it is not straight. Total distance traveled, so I'm going to go through, I'm not moving here. From 30 down to negative 10, you'd be going down 30, and then another 10, so you'd be going down 40 meters. 0 here, negative 10 to 0, you'd be going up 10. So total distance, add them all up, you get 50 meters. Displacement, we care about start and finish. So my starting position was 30, my ending position was 0. So I started at 30 and I ended at 0. I just went back 30 meters. My displacement would be negative 30. At 2 seconds, we already said that this was at rest, so your velocity would just be 0 in that time. And instantaneous velocity at 3.5, well, that would be this green section right here. V equals d over t. Remember, we cannot find velocity for a point, but I can do it for a section, so I'm going 40 meters. And the time that it took, 3.5 just tells me what section to look at. I'm still looking at the time for the section, which was from 3 to 4, which is 1 second. And technically it's backwards, so that would be like down negative 40. So that would give me my speed or my velocity of negative 40. Alright, which of the following pairs is correctly matching speed and distance graphs or position and velocity graphs? Here, you'll notice that it's getting flatter. This would be getting slower, which means my velocity would actually be decreasing. So A is incorrect. B, again, we said that would be getting slower, so not speed increasing. That's incorrect. This one's actually at a constant velocity, which means my speed would actually be staying the same, so incorrect. And then this one, so this one is getting steeper, and then this one is also getting steeper. These will never be the same. This one getting steeper means that my velocity is increasing. I'm getting faster and faster, so my speed should be increasing, so E is the correct match. Number 10, we've got a ball that's dropped from rest from the top of a building, strikes the ground with a speed of 30. Gravity is this acceleration. What is the height? So if we are dropping from rest, that is my initial velocity would be 0. This speed is the speed that it's hitting the ground with, so that would be like my final velocity after it's accelerated, be final. This right here is my acceleration, because it says meters per second squared, and I'm looking for the height. Height would be like your distance traveled, measured in meters, so distance is my unknown. So if I have A, VI, VF, and distance, the equation that has those 4 letters is our last one. So we've got 30 squared equals 0 squared plus 2, 9.8d. And then now it's just cleaning it up. So 0 squared is just 0, that's plus 0 is going to go away. 30 squared is a number, so you put it in your calculator and you get 900. 2 times 9.8d, well, I can just multiply these two and I'm going to get 19.6. And that distance is still there, right? Your unknown didn't go away. Now the last step is trying to get d by itself. I'm going to divide the 19.6 over. And put that in your calculator. You should be getting your distance is like 45.92. And then now you're just using the best answer. Oh, that's basically 46. Circle, move on. A bird is flying in a straight line. Initially at 10 meters per second, it increases its speed to 18 while covering a distance of 40. What is the magnitude of the acceleration? So let's look at this initial speed or initial velocity. That's the velocity after my final velocity. I cover a distance of 40 meters and I'm looking for acceleration. So same equation because I still have both velocities, distance looking for A, last equation. VF is 18, 10, 2, A is what I'm looking for, a distance of 40. All right, 18 squared is just a number, 324. 10 squared is 100. And then 2 times A times 40, well, that's just going to be 80A. So I can multiply those. Now, careful, I cannot combine the 100 and the 80 because those are not like terms. So I need to get rid of this 100 first. I'm going to subtract the 100 over. That's going to give me 224 equals 80A. And then now we just divide the 80 over so that we can cross it off and A will be by itself. I get 2.8 and that is your answer, D. 12, position versus time graph for an object is shown. What is its instantaneous velocity at 2? Now it's very tempting to go, oh, 2, it's at 0. That does not mean it's not moving. That's not a velocity of 0. That just, in fact, we know it's moving at a constant velocity here. That just means it happens to pass the 0 meter mark. We still find velocity the exact same way. V equals d over t. You can do it for the whole thing. You can do it just for the first couple seconds. It doesn't matter because it's the same slope either way, right? It's the same rate. So I just did it for this little section right here. 4 to 0, I'd be moving 4 meters, and it would take 2 seconds, and it would be a minus, right? Because I have to choose between a minus or a plus sign, and it's minus because I'm going backwards or down, so that is minus 2 meters each second. You also could have done it from 4 down all the way down. That's fine. 4 to negative 2 would be negative 6 meters, and it would have taken 3 seconds. So yeah, we'd still get negative 2. All right, the acceleration between 60 and 120. So 60 and 120, I'm looking, I have a velocity graph. So I know my velocity is my time looking for A. That is this equation. VF would be 30. VI would be 10. A is what I'm looking for, 60 to 120. That's a difference of 60 seconds. Now I have this 10. I'm going to subtract that 10 over. That gives me 20 equals A times 60. To get A by itself, I divide the 60 over. And that gives me 0.33 B. Here, again, I'm trying to find matching graphs for position and the velocity graph moving forward. There are multiple answers. So here, this is going forward at a constant velocity, so I have a constant velocity, A. B is going backwards at a constant velocity, so I have a negative velocity, and it is constant. That is true. This one is moving forward, but getting slower, so that's getting slower. Velocity should be slowing down, so that's true. This one's moving forward, getting slower. Velocity should not be increasing. This one is a constant velocity, so my velocity should not be increasing, it should be staying the same. So these were the 3 that have correct matching graphs. A coyote accelerates from 10 meters per second, that's my initial velocity, to 35 meters per second, that's my final velocity, in 20 seconds, that's my time, and I'm looking for how far. Now, if you look for an equation that has those 4 letters, you're actually not going to find one. This is one of those 2-part ones. I'm going to have to find something first, and the thing I have to find first is acceleration. So I'm going to use VF equals VI plus AT. 35 equals 10 plus A times 20. And then now I'm going to subtract the 10 over. You have 25 equals 20A. And I'm going to divide the 20 over, running out of room. So that gives me an acceleration of 1.25. Now that is not my answer. I'm still asking for how far I travel, and I'm still asking for that distance. That just happens to be an acceleration, which I'm going to need. Now I can use either equation that has distance in it. I picked this one because distance is already solved for it. I'm not going to have to rearrange the equation or move things around. And then now it's just plug and check. VI is 10. time is 20 plus 1/2 acceleration we just said was 1.25 times time of 20 squared, and then type that into your calculator and you should be getting 450. We have a velocity versus time graph, and we are checking to see which of these is incorrect. So first statement, the car is moving fastest at 2 seconds. So on a velocity graph, the fastest would just be literally the most velocity. At 2 seconds, yeah, that is the highest velocity. This is like, what, 15, which is higher than all of the other ones. So yeah, that's true. It's at rest, approximately at 1.5. Well, rest on a velocity graph would have to literally be at v equals 0. So see how just after 5 you actually are at v equals 0? So yes, it is at rest for that instant. It's speeding up from 0 to 2. 0 to 2, my velocity is increasing, that is true. It's at rest at 2 seconds. No, it's not. In fact, I have a velocity of 15. Rest would be velocity of 0. So D was the incorrect or the false statement. We've got a plane that is traveling 900 meters per second south to an outside observer. So I'm going to draw this. To an outside observer, the person on the plane seems to be moving at 903 meters per second south. So looks like 903 meters per second down. So the person on the inside, let's think about, if the plane is only moving at 900 and it looks like they're moving even faster than that, that means they're going in the same direction. So they're definitely going like south as well, or towards the front of the plane. And then if the plane is actually at 900 and they look like 903, then that means that they must be walking at 3. So you could say 3 meters per second south, or you could say 3 meters per second to the front of the plane. Either way, I know that you know that it's in the same direction as the plane is moving. And then you double check. So if this were the case, you would say, oh, 3 towards the front of a 900, you would add to get to 903. Yep, that checks out. We've got a bunch of races with distances and times, and I want to find the fastest average speed. So let's actually calculate the average speed. That would be v equals d over t. 200 meters in 113.73 seconds. Now I just divide, that's 1.76. The next race would be 400 meters in 236.46 seconds. That's going to be a speed of 1.69. And my last is 800 meters in 483.79 seconds. That gives me a speed of like 1.65. So the question was actually which one had the fastest average speed. So now I'm looking. The fastest speed would be this one right here. The 200 meter race is the fastest average speed, because 1.76 is faster than the other two. The velocity versus time graph, what can we conclude? So going up on a velocity graph is speeding up, and then going down on a velocity graph is slowing down. So then that doesn't work like the word slowing, that's okay. So speeds up followed by slowing down, B. The first 25 meters of a 100 meter dash are covered in 5 seconds by a sprinter who starts from rest and accelerates with constant acceleration. The remaining 75 meters are run with the same velocity. I want to find their constant acceleration in the first 5 seconds. So I'm just looking at the first 5 seconds, so t is 5. And it says I only covered 25 meters. The whole race is 100, but the first 25 meters were covered in the first 5 seconds. That's the second part. So I'm going to use distance is 25, because that's the distance that goes with this time. It says starts from rest, so initial velocity is 0. And constant acceleration, so I'm looking for that constant acceleration. I've got d, vit, looking for a, so that is the d equals vit plus 1/2 at squared equation. Distance is 25, 0 goes away, 1/2 a is what I'm looking for, time is 5 squared. So I've got 25 equals 1/2 a, 5 squared is 25. Half of 25, that's just 12.5, I think. Yeah, I'm pretty sure. Right, and then now I just divide over, and that's going to give me an acceleration of 2. B is asking for the sprinter's velocity after those 5 seconds. Finding velocity after would be VF. I would not use v equals d over t right now, because for the first 5 seconds I actually have an acceleration. It's not constant velocity, so I wouldn't use the v equals d over t. Looking for VF, so I can use either VF equation. I picked the time one, so I don't have to square root at the end, but it's not a big deal. Initial velocity was 0, acceleration we just said was 2, and 5 seconds is our time, so my final velocity would be 10. C is like the C from the warm-up. I'm actually going to cross it off, so if you don't do it, it's not a big deal. On the position versus time graph, shown which car is moving at a slower speed and why. So this is A, B, and this one got cut off, but you can probably figure out that we would call that C. So of these, the slower speed. So we know that speed is just like how fast it's moving, right? How much distance it's covering each second. And we know we can find velocity or speed from the distance graph as the slope, doing the position over the time. So the slowest one is the one that has the least slope, or the flattest. So the flattest one was C. So this one is the flattest, or it has the least slope. The steepest one, the most vertical, would be the faster one, because steeper is faster on a position graph. So A would be the fastest, C would be the slowest. Which of these intervals is the speed changing? We're looking at a distance or a position graph. So where it's curved is where the speed is changing, so that would be D to E. We want matching distance graphs. So distance flat would actually be at rest. You'd have to have a speed of 0, so that's not it. This one is slowing down because it's getting flatter, so I would need my velocity to go down, so it's not this one. This one is getting steeper, which means it's speeding up, so I need my speed to be going up, so that works. This one would be constant velocity backwards, which means my speed would be constant, would just be negative, so not that one. Instantaneous velocity at 5 seconds. At 5 seconds, this is flat. It is now at rest, so your instantaneous velocity in that little section right there would be 0. Car is going at 10 meters per second, so that's my initial velocity. 4 seconds later, that's T. It's going at 18, so final velocity would be 18, and I'm looking for acceleration, so I'm just plugging into that VF equals VI plus AT. 18 equals 10 plus A times 4. Subtract the 18 over first, that gives me 8 equals 4A. Divide over, you get A is 2, and we're looking at acceleration, so that would be meters per second squared, D. Baseball pitcher warming up when they're traveling to a game by plane. The plane itself is going 150 meters per second east relative to the ground, and the pitcher, who is inside the airplane, throws the ball at 30 meters per second relative to the airplane. If they throw it to the front, it would look like this. If they throw it to the back, like in situation B, it would look like this. In each case, I want to know what the velocity relative to Earth, so like what somebody outside on the ground would say that the speed looks like. Well, these two would just add together. That would look like 180 meters per second east. These two would subtract and it would look like just 120 meters per second relative to ground. And the challenge you do not have to do. If you really want to know how to do it, you'll come in. You can come in and ask because I'm not going to put it on the video. Study.